A profound shift is occurring deep within our planet. Thousands of kilometers beneath your feet, in a place hotter than the surface of the sun, the very heart of our world is changing. For generations, we believed the Earth's core spun in a constant, predictable dance. But recent, groundbreaking evidence suggests that this dance might be slowing down, perhaps even stopping. What does this mean for us, living on the surface? This isn't just a geological curiosity. The core is the engine of our planet. It generates an invisible shield that protects all life from deadly solar radiation. It dictates which way our compasses point. Its stability is fundamentally linked to our own. So what happens when that engine starts to behave unpredictably? To understand why these changes matter, we first have to take a journey. Forget everything you've seen in Hollywood movies. We can't drill to the center of the Earth. The pressure is millions of times greater than at the surface, and the heat would vaporize any machine we could build. So how do we know what's down there? The answer is with earthquakes. Every time an earthquake happens, it sends seismic waves vibrating through the entire planet. They are like a planetary scale ultrasound. Some waves, called P waves, can travel through both solids and liquids. Others, called S waves, can only travel through solids. By studying which waves make it to the other side of the planet and how they bend and slow down along the way, seismologists can create a detailed map of Earth's interior. This is how we discovered that our planet has a layered heart. At the very center is the inner core, a solid ball of iron and nickel about the size of Pluto, with a temperature of nearly 6,000 degrees Celsius. Surrounding that is the outer core, a vast ocean of liquid iron and nickel, thousands of kilometers thick. It's this liquid outer core that is the source of Earth's most important feature for life, its magnetic field. Imagine a giant, churning, electrically conductive fluid. As the Earth rotates, the liquid metal in the outer core swirls and spirals, creating powerful electrical currents. This process, known as the geodynamo, turns our planet into a colossal electromagnet. This magnetic field extends tens of thousands of kilometers into space, forming a protective bubble around us called the magnetosphere, and we need it. Out there, the sun is constantly blasting out a stream of charged particles, called the solar wind. Without the magnetosphere, this solar wind would strip away our atmosphere, boil our oceans, and bombard the surface with deadly radiation. Life as we know it would be impossible. Mars was once a water-rich world, but its core cooled and solidified. Its dynamo died, its magnetic shield vanished, and the solar wind scoured it clean. Our core is the reason Earth didn't suffer the same fate. It's our planetary life support system, and that's why any change to it is such a big deal. So we have a solid inner core floating inside a liquid outer core. For a long time, scientists have believed that the inner core spins slightly faster than the rest of the planet. Think of it like a metal ball bearing spinning inside a fluid-filled casing. We could track this rotation using a clever trick involving those same seismic waves we talked about. For decades, seismologists have studied pairs of nearly identical earthquakes, called seismic doublets, that occur in the same location years apart. By comparing the travel times of waves passing through the inner core from these doublets, they could detect tiny changes. From the 1960s through the early 2000s, the data showed that the inner core was indeed rotating slightly faster than the mantle and crust, a phenomenon called superrotation. But then, around 2009, something changed. The data started to flatten out. The difference in travel times that had been steadily growing for 40 years suddenly vanished. In a landmark paper published in 2023, seismologists Yi Yang and Zhao Song analyzed decades of data and came to a startling conclusion. The inner core's superrotation appeared to have paused. It now seems to be moving in sync with the rest of the planet. Has the inner core stopped spinning? Not exactly. It's still rotating with the rest of the Earth. But its extra speed, its superrotation, has seemingly halted. Some models even suggest it might be on the verge of subrotating, spinning slightly slower than the mantle. The engine's rhythm is changing. So what could cause a Pluto-sized ball of solid iron to change its speed? The answer lies in a cosmic tug-of-war between two immense forces. The first force is electromagnetic. The swirling liquid outer core generates the magnetic field, and this field pulls on the solid inner core, trying to make it spin. It's like the spinning part of an electric motor. This force is what scientists believe caused the superrotation for decades. But there's another, opposing force: gravity. The Earth's mantle, the thick layer between the core and the crust, isn't a perfect uniform sphere. It has massive, dense structures within it. These structures have their own gravitational pull. This pull acts like a brake, creating a gravitational coupling that tugs on the inner core, trying to slow it down and lock it into place with the mantle. The current theory is that we are witnessing a shift in the balance of these two forces. For several decades, the magnetic torque was winning, and the core was speeding up relative to us. Now it seems the gravitational coupling is reasserting itself, slowing the inner core back down. This isn't a one-time event. Scientists believe this could be part of a cycle, an oscillation that happens every 60 to 70 years, where the core speeds up and slows down again. We just happen to be living through a moment of dramatic change in that cycle. Okay, a 70-year cycle in the core. That's fascinating for geologists, but does it actually affect us up here? The answer is yes, but in very subtle ways. The core is not mechanically linked to the mantle and crust, but it is coupled through these immense forces. A change in the core's rotation could have tiny but measurable effects. One potential effect is on the length of a day. The total angular momentum of the Earth's system is constant. So, if the inner core slows its spin, to conserve momentum, the mantle and crust on the outside might have to speed up ever so slightly. We're talking about changes of thousandths of a second per day. These are tiny fluctuations, but they are crucial for things like GPS, satellite communication, and astronomy, which all rely on precise timekeeping. Another effect could be on the magnetic field itself. The inner core plays a role in stabilizing the geodynamo. As it grows and solidifies over billions of years, it helps power the convection in the outer core. If its rotation cycle influences the fluid dynamics of the outer core, it could contribute to small, decade-scale variations in the magnetic field that we already observe. These are known as geomagnetic jerks, sudden changes in the field's behavior. These are not apocalyptic changes. This cycle won't cause earthquakes or volcanoes, but it reveals a deep, powerful connection between the planet's heart and its surface that we are only just beginning to understand. This short-term cycle is fascinating, but it points to a much bigger, more dramatic change the core is capable of, a full magnetic pole reversal. The geologic record tells us that every few 100,000 years, on average, the Earth's magnetic field weakens, becomes chaotic, and then completely flips. North becomes south, and south becomes north. We are long overdue for one. The last full reversal was about 780,000 years ago. What does this have to do with the inner core's spin? We don't know for sure, but the processes are linked. A reversal is the ultimate sign of instability in the outer core's dynamo. The inner core's steadying influence is crucial. While the 70-year oscillation we're seeing now is not a sign of an impending reversal, studying it helps us build better models of the geodynamo. The more we understand these small changes, the better we can understand, and perhaps one day predict, the big ones. A full reversal would be a major event. During the transition, which could take thousands of years, the magnetic field would weaken significantly, perhaps to just 10% of its current strength. Multiple north and south poles could pop up all over the globe. Our protective shield would be at its weakest. This wouldn't be an extinction-level event. Life has survived many reversals before, but for our technological civilization, it would be a huge challenge. Power grids could be vulnerable to solar storms, satellites would need extra shielding, and navigation systems that rely on the magnetic field would be useless. Understanding the core is key to preparing for this eventuality, however distant it may be. The story of Earth's core is a story of constant, slow evolution. It wasn't always like it is today. Scientists now believe the inner core only started to solidify about 1 billion years ago. Before that, the magnetic field may have been much weaker and more unstable. The birth of the inner core may have been the event that supercharged the geodynamo, creating the strong, stable shield that allowed complex life to flourish on the surface. And it's still growing, by about 1 millimeter every year as iron crystallizes out of the liquid outer core. Every change we see, from the 70-year spin cycle to the long-term process of pole reversals, is part of this grand planetary evolution. We are living on a dynamic, breathing world, not a static rock. The changes in the core are a reminder that the forces that shaped our planet are still at work, constantly reshaping its future. So the next time you use a compass, or see a stunning aurora in the sky, or simply enjoy a warm day under a blue sky, remember the churning metallic heart of our planet, thousands of kilometers below. It is not a distant, abstract concept. It is the engine that makes our world possible. And by listening carefully to the faint, seismic whispers that travel through it, we are, for the first time in human history, beginning to understand its deep and profound secrets.